In this video, we're going to discuss the distance between 2 points, P sub 1 and P sub 2, each with their own x, y, and z, how to determine the distance between those 2 points in a 3 space. And here we have our formula. We've got these bars, and moving forward, because we're going to be talking a lot about vectors, these bars mean magnitude. Magnitude is the same as length or distance. So the magnitude from P1 to P2 equals the square root, the difference of my x's squared, plus the difference of my y values squared, plus the difference of my z values squared. So this formula is very similar to if we were dealing with 2 space. If we had 2 points just in the xy plane and we were trying to determine the distance between them, it would be this abbreviated portion of the formula. Of course, we're dealing with 3 space, so those z values are added in there. Now let's examine the proof of how this formula in 2 space also applies to 3 space. I'm going to bring in a picture. What I've brought in is a picture of a construction of a rectangular box with faces parallel to the coordinate planes. We have the points P1 and P2, P1 and P2, at opposite corners of the box. So we've got the lower rear and the upper front. Okay, and this is on the left, this is on the right. So completely opposite corners. And then we have points A and B. They're the vertices of the box indicated here in the pic. So if we take these 3 box edges, P sub 1 to A, which is down here, A to B, and then B to P sub 2. So we're looking at 3 edges, and each edge is a line in 2 planes. If we went to consider the magnitude or the length of just PA, that would be the difference, and I'm using absolute value bars here because we measure length as a positive value, x sub 2 minus x sub 1. If we look at the magnitude of AB, we would have y sub 2 minus y sub 1. And if we look at the magnitude of BP sub 2, that would be z sub 2 minus z sub 1. So now let's consider the fact that we have 2 triangles in here. I have one triangle right here that I'm highlighting in purple. This triangle, we've got triangle P sub 1 to B to P sub 2. That's a right triangle. We also can visualize a triangle from P sub 1 to A to B. So I have these 2 right triangles, P sub 1 to A to B. One lays on the base, and one is diagonally through the center, standing up vertically in this rectangular prism. So these are both right triangles, and because we have right triangles, we can apply our Pythagorean theorem. So what we can say P sub 1, P sub 2, that length squared, equals P sub 1, B squared, plus B P sub 2 squared. So that's our Pythagorean theorem. Hypotenuse squared equals the sum of the 2 legs squared. Similarly, for that base triangle, that hypotenuse would be P sub 1 to B squared equals P sub 1 A squared plus AB squared. So let's look at this. P sub 1b quantity squared is the same as that, which means I should be able to substitute those two terms in for that one in the purple equation. Let's rewrite that. We've got P sub 1, P sub 2 quantity squared equals P sub 1b quantity squared is equal to P sub 1a squared plus AB squared. And then we've got plus BP sub 2 squared. Now, you'll note up here, I identified those three lengths. P sub 1a is the difference of my x's, AB is the difference of my y's, and BP sub 2 is the difference of my z's. So I have P sub 1, P sub 2 squared, the difference between my 2 points. P sub 1a quantity squared is the same as the difference of my x's. AB squared is the same as the difference of my y values. And BP sub 2 squared is the same as the difference of my z values squared. So because these are all squared, we do not need absolute value bars anymore. And if I look at the inverse operation for this square, canceling it, that would create a square root on the other side. Therefore, we can write P sub 1, P sub 2 is the square root of the difference of my x's quantity squared plus the difference of my y values squared plus the difference of my z values squared. So that's our proof. That's how we can develop the distance formula between 2 points in 3 space. Let's look at applying this now. Here we're going to apply the distance formula and find the distance between the 2 points that are given. So the distance, or the magnitude of that length from P sub 1 to P sub 2 is going to equal the square root of the difference between my x values, 2 minus negative 1, 2 minus negative 1 squared, plus the difference of my y values, 5 minus 1, quantity squared, plus the difference of my z values, 0 minus 5. And that gives me the square root of, I get 3 squared plus 4 squared plus 5 squared, which simplifies to the square root of 50. Of course, we can simplify that. 25 comes out and we get 5 root 2. So the distance between both of those 2 points is 5 root 2 units. Now we're going to talk about the distance formula and how it's used to write the equation of spheres in space. Here we have the standard equation for a sphere of radius A with a 3-space center. And this looks, again, very similar to our 2-space equation of a circle. If you take a circle and you make it 3-dimensional, that would become a sphere. So we've got the difference of our x's squared, the difference of our y's squared, the difference of our z's equals a squared, and a represents the radius. So as long as we have a 3-space point and a radius, we can develop the equation of a sphere. For our last example in this video, we are given the equation of a sphere and we're asked to determine the center and the radius. In order to do this, we're going to use our completing the square process. So I'm going to organize my terms. I've got x squared plus 3x, and I know I'm going to want to add some term to complete the square, plus y squared. Since I don't have any more y terms, I can just leave that, and then I've got plus z squared minus 4z, and again, we're going to need to add a term when we complete the square. That is going to equal -1, and whatever I add on the left, I have to add on the right to keep this a balanced equation. So when we go to complete the square, this term is always found as b divided by 2 quantity squared. B in this case being 3, I have 3 over 2 squared, or 9/4. So I'm adding 9/4 to both sides of the equation, as well as -4 over 2 quantity squared, or -2 squared, 4. So what this looks like as I simplify it, I have x plus that 3/2 squared plus y squared plus, we have z minus 2 squared, and I had -1 plus 9/4 and plus 4. Simplifying the right side of the equation, this value is 21 over 4, so I'm just going to erase that and write 21/4 in there. And our center is -3/2, 0, and +2. And the radius is going to be the square root of 21 over 4, which would simplify the square root of 21 over 2. So now I have a radius and a center. So my a value, this was a squared. I had to take the square root of it to find a for my radius. And then because the standard form has minuses, these values for 3/2 and -2 are the opposite in my center. So just to recap, we talked about the distance between 2 points in 3 space, as well as the equation of a sphere in 3 space. If you have any questions, please feel free to email me and ask for more resources.